If you're really looking here at the walking part, hmm, that's a little bit different. And really, what's the big deal? And I think the big thing is not so much that the abduction is not where it should be, is that the rotation is not where it's supposed to be. The rotation should be over here more in the middle. And this is the key to like the difference between humanoid walking and human walking, and why the solutions will probably vary a little bit. So Unitree is actually pursuing both designs simultaneously. That's interesting that, they didn't really abandon RAF. And again, if we overlay the two, we begin to see that they were onto something here, but they messed up. And that their rotation is too far inboard. It's but in some ways they almost got it right. The first time I ever saw this was from P&D Botics, and this is their Bot. And it was kind of intriguing. It's like, okay, why did they go ahead and do that? I wonder why that's there. And it's a really strong angle. I mean, it looks like it's about 45 degrees. They they maybe were inspired from that, but did it for the wrong reasons. I'll show you kind of why and the problems that this kind of causes. I took our Decimate, remember our Decimate robot, and I put in a 45-degree anhedral angle here. And we can go ahead and look at what happens when I just rotate the the F actuator. Okay. So when that happens, look what happens to my leg. It has to stay in this plane. The rotational axis is in that plane. So everything rotates from that plane. And you'll see that everything gets really screwy. Okay. So hello, Nara. How are you doing today?
Good.
Okay, so are you ready for another episode where we're going to kind of look a little bit at what human bots are doing?
Yeah, I'm so excited. I think the latest two episodes, people enjoyed it.
Okay, well, this one I've decided to call Walk This Way. And some of you may remember that as a 1975 chart topper from Aerosmith. But part of it is that we've seen some reinforcement learning used in walking recently. A couple of videos that are out there that make it really interesting to see how are we actually teaching robots to walk, and that seems to be a question that's been coming up quite a bit. And so we're going to try to examine that. But before we do that, and let me just go ahead and share my screen here, and we can take a look at what's going on in the world. But before we do that, I think we want to take a little bit of a review of what we did the past 2 weeks. Do you remember what we talked about in the last two episodes?
Yeah, it's all in the hip and the waist, not
Yep.
want. Yeah.
Right. Right. And so remember, let's talked about different kinematic configurations that are there and everything, and sort of implied what they may or may not be good for. But now may be a good time to kind of tie a bow around the whole thing and sort of see it. How does it actually affect walking styles, and where it's going to be in there? And so that's why I've shifted away from like focusing on shoulders this week, which will happen lovely next week, and kind of get more into that, looking at what's going on. So here we go. Let's see, Walk This Way. And we've got two videos that came out the past 2 weeks looking at this. And of course, there have been a lot of other videos and everything else. But one is from Figure, which I think is pretty interesting. Also, another update from Tesla showing what Optimus is doing. We're going to try to compare the two and then do some actual analysis. So we'll just take a look at the very first video. And this is the one that came from Figure. And let me just mute that a little bit, showing the update that they did. So if you look at this walking comparison, and I'm just going to stop it briefly because we all might remember that it really had bent knees. It was never very straight. And if you look at the steps, they always say one step in front of another, 1 foot. It's like it's barely 1 foot in front of another. Actually, it's not. It's not even a full foot length that you see as it's walking around here. And that was the old way. And now look at this. I mean, you actually have a full stride where the feet are clearly going way ahead, much faster, much smoother, far more erect. And it's coming from that they did simulation, and from the simulation, moving it into the real. And there's a lot that has to be done to get that to work correctly. But using reinforcement learning, you can then take it, and then here's an actual fleet of 10 figure bots, the F2s, showing that they are able to take this into real. And that was not CGI. Those are real. And again, we get pretty good idea what the hip motion looks like and the waist motion and everything else and importance and what that's kind of be in walking. So that's just a little bit of teaser of what we're going to try to analyze. And then if we take a look at the next update, and this one is also from now from Tesla and showing walking with their reinforcement learning. And what you might be able to see here, and what we can kind of glean from this is as far as the speed, style, and everything else. So we're going to try to analyze the different gaits of these bots side by side to get an idea of what's going on. Unfortunately, that's the most we got. We got a more detailed update from Figure, which I think is good. Just a general idea of how reinforcement learning is being used when it comes to walking. And these aren't the first two to do it. Well, most of the Chinese bots have been doing this for like well over a year. And it's almost like, oh, okay, they're finally getting the game and maybe getting the game a little bit late. So we want to do gait analysis. And the first thing I want to do is I want to give a shout out to Physical Therapy Education Solutions. There's a series of videos out there that they've done. Some of them are about 4 years old that are really maybe targeted for people who are going to be physical therapists by talking about how you analyze people's gaits and different motions to see what the problems are and what kind of exercise you would need. And it's absolutely excellent. And let's say, unlike our videos, they're maybe a bit more digestible and that they're all less than 10 minutes, but they're really well produced and they really give you a great idea of what's going on. Even if you're not familiar with the terminology, you will pick it up very quickly. So it's not really heavy in jargon, but gives you sort of an idea of what's going on. And these are the three main videos looked at. They have videos for all sorts of other things that would be like, straightening your back out exercises. That'd be good for that. But if you just want to understand the theory of walking and gait analysis, is absolutely excellent. And I've taken a lot of clips from here as the reference that we're going to use. So this is a really good guide. Please go there, subscribe, look at the videos, like them and everything else, leave some comments. They'll probably suddenly go, why is a sudden spike of like people viewing our videos after 4 years? Well worth it. So the first thing we're going to do is we're going to look at the motion in the sagittal plane, which is just a fancy word for basically the side view. Okay. So if we go into the side view, we can take a look at different phases of the gait that they describe here, that you have like a stance phase and a swing phase. So the stance phase is pretty much when your feet are planted on the ground. And you're kind of standing. And the swing phase is like when one of those legs comes off and you start to go through. And it's obviously you can break them down into the like initial, mid, terminal parts of the swing. And so they are looking at a lot of those things because this is important from the standpoint of loading curves, the kind of motion that's going on, all the other abduction and rotation that may have to be going on to compensate things that are going down here in the ankles. And so they break this down really pretty well to really nerdy things where you can begin to look at like just one axis of motion here. And this plantar flexion and dorsiflexion is referring to pretty much the pitching motion of your ankle. Your toes going up and your toes going down in that side plant, and then looking at the various locations of where the motion might sort of turn around and change and how far you need to go. So this is kind of a plot of that you would try to look for over time. And from that, and they have a video showing all that, in which I took the key points that are in there and that they go and they sort of analyze what these angles should be. So the first thing they're doing is they're looking at the lower leg and they're looking at it, when you get that initial contact there. So the heel is just starting to strike. What should your ankle angle look like here? So that's just the near neutral position. And then as you start to move forward, it's called slight plantar flexion, which means you're kind of pushing down a little bit on your toes because you can kind of see the toes were pointed up here and now you want to flatten them out. And then as you kind of go through, then you get this dorsiflexion that now your toes are kind of being pushed up because that's what you got to do to maintain contact as you go back. I mean, it's just pure geometry at that point. To finally where you get the push off here, you get that toe off and looking at what that angle is right here, and then the movement back. So now you're kind of do your return stroke, and at some point you need to go away from having this plantar flexion to more of a dorsiflexion to make sure your toes don't drag along the ground. There's two ways of doing it. You can either lift your knee up, bend your knee more so your foot doesn't hit the ground, or you can like just move your foot out of the way. And so that's the natural way that we're doing that. So now I took the side views, the best side views I could get from F2, and tried to label them the same way to get an idea of how much it matches up to human gait. And you can see it's not too bad. The only place that I think it's not so good is right here. And any idea of why it kind of fails? in this, let's say, fourth position.
I think that the foot itself seems
Yeah.
rigid.
Yeah,
Mm.
yeah, yeah. I mean, and this is the problem with all robotic feet is the feet are just planks. They don't have any flexion in the toe box. Now, you don't need to put a degree of freedom in there in the sense that it has to be actuated, but you could put a compliant joint in there that would make a lot more sense because you can see it's pure like, the toe box here is kind of staying flat and that allows you to get that plantar flexion and that actually allows you to get some propulsion. So that helps your stride quite a bit to get a bit more oomph out of it. So now you're able to get it not just from your flexion or from your knee, but you're actually allowing your ankle to give you that little bit extra push. There's another reason that I would like to see robotic feet have some sort of compliant joint in there. And that is it's a pure math problem here. Is that think about it, you've got a flat surface on a flat surface. So your contact here is surface to surface contact. But as soon as you've got two choices. You either lift your foot straight up or more normally you're going to angle a foot. And as soon as you angle it so that that surface is no longer parallel to that surface, your contact goes from surface to surface, from surface to edge. And mathematically, that means you have no surface area in contact with the floor, which means there's just like you cannot, you're just going to slide. There's no friction or anything there in a sense. And so you go from having like really good contact to suddenly virtually zero contact there. You can't push on it without that foot sliding back. So that's a bad contact point. Whereas you can see what the human foot does is it transitions from having like a lot of surface area to smaller amount of surface area, but you still have some surface area that's there that's able to maintain the friction that you need on the ground to be able to get that push off. So that's kind of two reasons for it. One is to maintain that contact, and second, also to allow you to take advantage of what is the plantar flexion to be able to propel you a little bit forward. I think the other thing we can look at, and that it'll become a bit more clear when we go to the next slide, is kind of okay. So we'll do the. Let me just jump. I'll come back to Optimus in a second here. Is if we look here at the full, the leg extension itself. So now here's like comparison, basically the same thing. Okay, so what we have here now is that we can look at that and we can see. So where's the room for improvement? So the first thing is like you just said, the flexible toe box would be nice. The other is that to actually, even though they're getting more of a straight leg, it's not quite as straight as human, and as a result, the stride length is not there. So more stride length means you're going to get more speed. So the speed of the figure bot is a little bit higher. I think I did a rough calculation. I forget what it was. It's not quite 2 miles per hour. It's but getting close to that, which is a lot closer to the actual magical speed that you want. So there's going to be improvements there. You can see that, but that stride length could also be a function of your back stride. So you just can't make your front leg go out further without also your back leg having to do the same thing. That's how you increase it. And if you don't have that flexion in your foot, that may be preventing you because when that's down there, you can only bend that ankle so much in the dorsiflexion, and you'd rather have plantar flexion going on there to kind of raise it up. And so that's going to limit you. So having a flexible toe box will probably not only be good for energy, but will also allow this to extend out a little bit further. So again, we can kind of do the comparisons of where it compares to the human and say, oh, right here, let's make that a little bit further up. But everything else seems to be pretty close and pretty reasonable when you look at that. And of course, what I should have done is like, they also have a really nice graph showing deflection extension as a function of percentage of the gait as you go through to see where it should be to get an idea on the different phases. Okay, so let's go back and then kind of look at Optimus. Unfortunately, I didn't have like really good views of Optimus. It's like off at an angle, so we don't have that nice sagittal plane or side view. So, and also was like walking the wrong direction, so I had to mirror the images to be able to get them to line up. And so it's really hard to tell exactly what the angle is here, but it kind of looks like it might be close to a neutral angle. It's the toes are kind of up off the floor. Now it looks like it sort of comes down, so right there. Here it looks like in that stance that might be a bit extreme. As up here it's about 10 degrees, but it looks like it should be a little bit. It's a bit more. And then we're coming up. You see the same problem that figure has is it's not opening up. It's even almost worse. There's more dorsiflexion than that plantar flexion that you'd want to have. And then when it's coming through, here it seems that you want to be near neutral, and they kind of might be as far as making sure the toes don't drag. So it's you get some sort of idea of what's going on there. And now again, we can then look at how Optimus is doing as far as the flexion that's going on in the comparison here. And again, it's kind of straight, but not as straight as it could be. Um, and kind of going back here, everything else looks about normal. But it seems like the Optimus stride is also not as big as it could be. They are getting the heels in front of the toes, and I think they've been doing that for a while. But still, it's a very kind of lackadaisical walk. They're getting kind of a long stride, but it seems like it's almost frozen in time when it goes through. So when I did the calculation, it's still not quite a mile per hour. It's like it it's hard to say if it looks better than they used to, um, but it's definitely not any faster because it seems to be about the same speed. So for some reason, I haven't been able to speed it up. However, the one thing I would say is that the arm swing looks probably better. That they have a much longer arm swing kind of going on there, which seems to correspond pretty well with the human arm swing, about where you expect it to be. And the figure arm spring seems to, there is some, but it's not as much as it should be. You see, it almost never goes in front of the waist. It's like just kind of hanging out down there, just moving around a little bit. So that's another place where figure would probably be able to improve with a little bit more arm swing. All right. And now, so I think we went through, oh, there's like one more. Where they want to kind of look at the again more the extension flexion. I think this is looking at the hip flexion. Okay, what's going on there? So before we were looking at the knee flexion, now we're looking at the hip flexion to get an idea of how that kind of stacks up. And it's kind of close, but maybe not quite. Again, the human gait, we're seeing that the backswing that we have there is a little bit more pronounced, and it's really hard without that nice kind of without a toe box here to get that back a little bit further. So you can see her leg is back further, which is why she has a much better kind of extension going on in the back there versus what we would see here. And then as you swing through, of course, you expect to get to kind of a neutral pose on the way. And then Optimus, it's sort of similar, which you might see there, so it's not too radically different. Okay. Now let's go to what is known as the frontal plane. And in the frontal plane, um, a lot of what they are looking at is what's going down the ankle to get kind of an idea of what's happening here with the different contacts that you're going to have. And some of these fancy words like, pronation and supination, which is really just kind of talking about your toes kind of moving in and out, and what and how you take the initial contact, because there's a lot of loading that's happening right at the point of initial contact. And your body does all sorts of things to absorb that load. So it's not just at the ankle or the foot, it actually goes all the way up through the leg. And the leg is kind of in a position to be able to accept that shock, um, and make sure that the muscles respond exactly the way they need to for that. So it's here what we end up seeing is that you get the supination version that they're kind of talking about up here, and then you get a little bit of pronation that kind of starts to happen here, and then back to supination. The pronation is going to be basically your toes kind of coming back in versus them kind of going out. So as you go through, you're going to have this kind of little bit of a motion on that's going on your ankle, and you can see it from the rear of the frontal plane. So it's a frontal plane, but the back part of it, there of exactly kind of what that angle starts to look like as you're walking along. And the thing is, I didn't have any good back poses like that from the bots to be able to compare back and forth. But it is something that would be interesting to kind of look at to see how the angle of the feet move as they go along from the standpoint of that particular plane. And then um, also in this plane, you can look a little bit at the pelvis. So we get kind of an idea here that as you're walking along, the reason you want the pelvis to be able to move. So you see there is this not horizontal angle there, is a lot of it is very important to being able to get the clearance of your foot. So so what's getting ready to go here is that the foot that's swinging forward, you don't want it to hit the ground, and part of it is to drop one side and bring the other up. like that when you're going around. So that's kind of a strategy that the body has, or we can see on both swings here how that is kind of going on to make sure that you're able to then get that swing through. So the and this is one of the strategies to have, and that's why you probably need to have also a waist, because if you move your pelvis this way, your whole body is going to turn. And if you want to keep your shoulders level, you then have to kind of counter that. And so that's the reason for having a waist joint in there, which would be in the X direction to be able to compensate for that. Okay, so hip initial contact, and then there are these other angles, which again are very hard for us to measure, but they sort of show a little bit of what is going on in the what is kind of the abduction that you would expect to see in the hips from like a neutral position to them kind of coming in to going out. So as you're walking your stride, there's almost like this in and out movement that the abductors are doing on that swing that is going to be considered, sort of an ideal gait. Um, okay, now this here is an interesting clip I just kind of caught for us to be able to see exactly that motion that we're talking about there. And we can see there's a lot of hip motion going on there, quite a bit of movement that goes in to make it possible for the feet to have the clearance and why it goes back. But if you look at the shoulders, if you look right at the shoulders, you wouldn't believe that there's that much kind of motion going on down in the hips. And that's because the waist is able to compensate for that. Um, I then took a really slow motion view here so we can kind of see exactly how the feet are clearing. And what you may not notice here is that you'll see that when it dips on the left side, so the abductor on the left side is trying to bring the hip down. And as it does that, the abductor on the right side seems to not compensate. And you'll notice the foot kind of swings wide. So as it starts to go out, that foot ends up kind of going a little bit to the side. So we'll see this again. So right here, as that drops, you see how that foot suddenly, rather going forward, you see a lot of that lateral movement. And that lateral movement, again, is because it's kind of dipping over this way. And it isn't trying to bring the leg back in. And that's what you think you would do, is that if you're bent, if you the abductor is giving me 3 degrees um, this direction, I would give also another 3 degrees that direction and would keep those two legs parallel. But that's not happening. So one of them is doing it, causing the other. And could be like another strategy that makes it very easy for walking and also increases your ground clearance. So you kind of get that ground clearance for free, and you don't need that abductor to kind of come back until you're ready to come down. And remember, this is reinforcement learning. So they're not saying it has to walk a particular way. We're going to get into that. They are putting some things in there to make sure it has a human-like gait, but it also has its own decision-making logic, or I guess not, it goes through in the optimization and decides, hey, this is like the best strategy for their energy or other reasons that are going on in there. So it's really interesting to see, let's say these, you want to call them emergent behaviors or emergent properties that come out from the motion. So sometimes you have to look at these things in slow motion to see what's going on. All right. Now, if we look here then at Optimus, we can get an idea. And we're seeing something really interesting here. So remember, we're talking about the pronation, the supination. If you really slow this down, this was like really interesting to me. You see that the foot almost slips there.
This.
Yes, you see how it starts to pronate, going on like that. It feels like an overpronation that's going on that is causing the foot to actually slide on the floor. I mean, to me,
And why is that? Why?
this
Why?
is interesting because there is no degree of freedom down there that would rotate below the knee. The rotation is happening up at the hip. So if you look at it, it's not just the foot that's moving; it's the knee suddenly bends in. And I'm not quite sure. And is that a way of compensating a little bit to get the extra propelling coming out of that? And again, this could be something that reinforcement learning. To me, it doesn't make sense that the knee would suddenly bend in like that so much. The other thing is, Mhm.
Quick question here, because this is done by reinforcement learning. So just
Yes,
associative movement, they came up with the best strategy.
yes,
But I'm just wondering, the engineer at Tesla, they didn't like notice this overpronation. It's very obvious.
yeah. And the other thing that's sort of interesting is is then look at the left foot that's in the air just before it strikes. You notice how it's kind of coming out on the edge and then coming in this way, and it's that's rather interesting. It's using the inner edge. Um, some people when they run, they it's more like the outer edge that we strike with, and then it flattens out. And instead, this is doing the opposite. It's doing the inner edge and then coming in. And there are people who run like that and they end up getting knee injuries because it puts a lot of twisting stress on the knee that way. So you come there with your heel strike and your foot may not be exactly parallel to the ground. It's going to be hitting a little bit with the outer part of the foot and then flattening out. So it's rather interesting. And we're going to get into maybe why it's doing things that are unnatural to us, and maybe why the engineers have seen this and say we don't care. And that's gonna that's sort of it's coming in. We'll have a discussion about that. But then the next thing you want to do is just look at the transverse plane, which is basically a fancy word for top view. So and this is why the waist is going to be very, very important. So again, this is from that same video series, in which they show a top view of when you're standing straight. You can see how the pelvis is not protracted, as it would say. So this is a protractor, and it's protracted or retracted, or the positive negative. That's how I remember this stuff. So what happens is that when you take a step here, you see the pelvis becomes protracted. In other words, it goes forward. The lead leg kind of brings it forward and the trailing leg kind of makes it go back. So the pelvis doesn't stay fixed, it goes. Now, if that happens, that means your whole body is turning. So when you walk, are you walking like this? No, we're keeping our shoulders straight ahead. And that means our waist has to counter rotate. Now, there's more to it than just the fact that we want to keep our shoulders facing forward. You actually want to have a reaction torque because by doing that, by this counter rotation, and of course, we know if you look at the arm swing, which I think we're going to see in the next slide here to get kind of an idea, they're sort of showing that if you look at the shoulder, you see your shoulders this way. And if you look at the pelvis down here, it's that way. So when it's protracted, the shoulder is retracted. And you'll see, the leg that's going forward, the opposite arm is going forward. And it's because the opposite arm is going forward, it's throwing a reaction torque to kind of keep the whole system in balance. So that's very important. And that the other thing about that reaction torque is it goes all the way down to the ground. And what that means is like the movement of your arms forward is causing greater force of that foot on the ground, which means it's able to push harder and stay contact a little bit longer and actually give you a little bit more forward movement. And this is one thing, and if you ever looked at sprinters, the best sprinters have a really well-developed upper body. You might say, well, wait a minute, what's the upper body got to do with sprinting? You think it'd be all in the legs. It turns out a lot of it is in the arms. Um, and that you can increase by up to 5% by having really good arm movement as far as your speed. So if you take your arms out, you actually lose a lot of that speed because your legs won't be able to push off as hard. So those sprinters, when they're coming out of the blocks, they are throwing their arms down, and you need a lot of strength to do that. Also, doesn't hurt to have a little bit of mass. So they throw that down, and that goes right down to the legs, which allows them to get out of the blocks a lot faster than someone who doesn't do it. So the arm swing is very, very important. And that's what we're kind of seeing here as well. That movement in the knee, we need a waist for that. Otherwise, that green line is going to be parallel with a red line. And again, you're going to be walking like this, which will seem a little bit silly. Okay, so kind of looking at that, there is a way looking, but again, using the more or less the sagittal plane to do this comparison because there was like no cameras from the top. The idea of how the shoulders and the waist are in different positions as you're walking. And you can see comparison with human and in comparison with figure. And of course, I'm eyeballing where these things are. So it's more or less like it's qualitatively correct. So it seems to be pretty close that the movement that you're seeing in the upper body corresponding to what you would expect. Okay, so now I want to get a little bit more into it. And what was interesting about the figure update, it wasn't just a video, but they also have an article that you can read here. that I recommend everyone go and read it because there's a lot of good information in there to explain exactly how reinforcement learning is working in the update. And as we went through it, there was like this point down here, which I'll read that says like, this includes walking with human-like gait, with heel strikes, toe offs, and arm swings synchronized with leg movement. We inject this preference into our learning framework by rewarding a robot to mimic human walking reference trajectories. Now, Chris Paxton like reposted this thing um, because when he kind of read that sentence there, and maybe I should probably read the whole paragraph and have it make it, a policy learned using RL might converge to suboptimal control strategies that do not capture the stylistic attributes that define human walking. So this includes walking with a human-like gait, heel strikes, etc. And when I looked at that again, I was almost like, oh, okay, is that necessarily the optimal strategy? And Chris put it out there. It's like, is this actually going to be more optimal? No matter how much these robots look human, they aren't. Motors aren't muscles, metal is not bone, etc. It seems artificial and suboptimal to reward human motion for a general purpose robot. Okay. And
So it's all you basically.
he's kind I mean, I definitely agree with many of the points he's making here. I did, of course, have to put my own reply in there in that I have maybe a slight quibble. Okay. And that is while I had similar thoughts, I would not jump to the conclusion that human-like motion is suboptimal as a starting point. This is an important starting point for RL. Nature is better optimizing than we are, and even if material and actuation strategy is different, bipedal motion has universal characteristics. So there are going to be some. And I think where we might have a little bit of disagreement is that I think using a human-like strategy is a way that you prime the pump. Chris McConnor argues says, okay, but it's also a way to poison the well. So, because it may be that there's some other strategy in there we're not aware of. So you have to be very careful how much you kind of force that. But again, let's look at sort of what they're saying is like, the benefit of humanoid robot is one general hardware platform that can do human-like applications. And over time, we want our robot to move more like a human through the world. Okay. So that's really the goal is we do want them to look human-like. So we're trying to design these structures to allow us to have human-like gait. And we believe these structures are going to do that. And it may turn out that they don't. And that's part of what Chris is almost arguing is that if we let this thing go, it may turn out that the optimal locomotion strategy for these things is that they crawl. Okay. It's like, well, wait a minute. That's not what we want. We want them to be standing up. So you inject something in there and say, okay, we're only going to reward the ones that have it standing. And the result could be something like, John Cleese in Monty Python in the Ministry of Silly Walks, where, your leg is swinging around and like doing all these weird things because that's the optimal strategy for that configuration. And we don't know that. We don't know that that's optimal. And in some ways, we do want to know that. So I would say let's get it up there, then relax it, and then see what kind of optimal strategy it comes up with. And if it comes up with one that is like just not human like, that doesn't mean there's something wrong with our RL. It means there's something wrong with the way we're trying to emulate the human physiology. Because Chris is right on point. Motors are not muscles. Bones are not made out of metal. So you need to kind of look at this as kind of a feedback loop to tell you, is our design strategy wrong? What do you have to do to make it more human? Because that's the goal. The goal is not to have some creepy thing moving through your space that, yeah, it's able to locomote, but you don't like the way it walks. You want it to walk human like. So we have to kind of figure that out. So again, I don't think we're in any sort of disagreement. It's just a question, what's the best strategy? Um, I would say priming the pump is the best strategy because you get results right away. Otherwise your RL, will require more computation and everyone's like, they want to get the results out as fast as possible. So I think it's an interesting point. And again, if we kind of look at the evolution of human walking that Tesla was looking at is this idea that first you're not having any the hips doing anything or the pelvis. And then you try to unlock it. And as you do that, you're going to get a little bit more and trying to go to toe. So they kind of know what they would like it to do. And that was being done more or less, heuristically. They were writing the algorithms for that as opposed to letting RL do it. And now RL is moving off in that direction and helping them out with it. Okay, so one of the things I want to do is remind everyone what the different hip structures look like that we have. So from and combining both the hip and the waist. So this is the Optimus waist, and we can say it's what we call ARF, which is mean they do abduction first, then rotation, and then flexion, which is the green down here. And then they're using pretty much the same servo kind of stack up here to do the waist. So you have like this X rotation, followed by the Z rotation that's going on up there. And this little Y, meaning that there is no actual Y through the waist. The whole Y of the torso is being accomplished through the flexion. So that's the multi-purpose there. And the figure waist is kind of similar, same idea here, but they're using rather than the ARF, they're using the FAR architecture here, where the one thing that you can kind of notice with this architecture is that all three axes intersect at one point right here. Whereas when you look here at Optimus, you begin to see, well, wait a minute, these two kind of intersect here, and then this intersects here, but all three do not have a common point of rotation. Okay, so that's one thing I want to point out. And then we can do like different, the side by side comparison here again to sort of see the little differences and how the flexion axis is further down for Optimus, but otherwise it's pretty much the same as far as the functionality. Well, okay, now and again, kind of looking at the differences here, but this is what I really want to get into. Is like Chris's point partly is that it's not it's not bone and motors are not muscle. But what we should really do is like really, really look at human kinematics. Forget about how the actuation strategy is done. Let's really look at how good we are doing at emulating the way the human body is able to do flexion, um, uh, abduction, and rotation. And it does it with a ball and socket joint. I pointed this out many, many times. So here's where the ball and socket joint is. And then the waist, it's more complicated than what I have up here. Let's say the rotation sort of starts up about here and continues way up the spine. So you could even move this up further to where it would probably be where your navel or belly button is. Um, but if we just concentrate on what's going on in the hip itself, we'll see that all three points of rotation are at the same location. So that's the first thing you really want to do. It's like, okay, we need to make sure that we get that common point of rotation if we want to emulate a ball and socket joint, even if we were doing it with three different servos to be able to do it. So, so we know that's how the human body is. And then again, reminder, this is how the figure two is set up. Let's overlay the two. So if you actually overlay the two on top of each other, you begin to see that, aha, okay, um, that only the red axis lines up. The blue axis, we see there's an offset, and the green axis, we see there's an offset. And then you also see that the rotation for the waist is way lower than it is in the human body. So that's a little bit different. But if you're really looking here at the walking part, that's a little bit different. And really, what's the big deal? And I think the big thing is not so much that the abduction is not where it should be, is that the rotation is not where it's supposed to be. The rotation should be over here more in the middle. And this is the key to like the difference between humanoid walking and human walking, and why the solutions will probably vary a little bit. I think they're going to be close. I don't think there's going to be Ministry of Silly Walk. Well, maybe a little bit. There may be like that swing that we saw with what figure was doing coming on out there. That may be something that the policy has determined is the ideal. And we think, well, that's a little bit funny. So if you saw someone walking down the road and their leg was constantly swinging out that way when they're walking, you'd say, oh, that's a bit silly. Um, but it may be that that's actually a perfectly good strategy for that kind of configuration. Again, uh, if we kind of remind ourselves what the Optimus hip looks like, and then also, again, what the human hip is, and then overlay them, we'll see that there's the same problem. There's this offset of the blue axis, but there's a really big offset with the red axis. So we should not be surprised that the walking policies of Optimus and the walking policy of Figure are going to be different because they're just kinematically very different. And because Optimus is so different to the human body, that weird thing we're seeing with the foot kind of sliding, that's coming from a rotation down along this axis. For some reason, it may be deciding that that is actually better for Optimus because it's not a human. It's a little bit different in the configuration. forget about the actuation strategy. I mean, like as Chris points out, it's like, we use muscles and the muscles do not line up orthogonally. They do a lot of other weird ways of being able to do it. So it's very, very hard to model um, muscles exactly that way. But if you just look at it from kinematically, it's already different. So you would expect the results are going to be slightly different. Now, here's the only one that I could find that was this RAF, which is basically rotation, articulation, and then flexion. And this comes from Unitary. This is their GR, or not, this is their H1 bot. And again, if we overlay the two, we begin to see that they were onto something here, but they messed up. In that their rotation is too far inboard. It's but in some ways they almost got it right because their flexion they kept up higher. Because remember, Optimus has got the problem. This red axis is way down here. And it's just like, oh, wait a minute. Now the light blue axis is like moved too far inland. So, but they're getting closer to, let's say, the way the human anatomy works there. They just kind of overshot. So it's sort of interesting to see there's now, as we know, the next generation of unit tree went to the far. So the H1 is using far. But what people don't realize is also, oh, sorry, the G1, the little guy that we see running around. There is actually an H2 out there right now, which is the next version of this. So Unitree is actually pursuing both designs simultaneously. That's interesting that they didn't really abandon RAF. They're like, oh, okay, we're still going to do it, and this is for our taller bot that we're having at, and they may see that there's some advantages to that. Now, I'm going to use a term that people are probably not heard of, and that is anhedral. And there's dihedral angles and anhedral angles, and it comes from aerospace. And everyone knows what a dihedral angle is because they're used to seeing it in an aircraft that the wingtips are higher at the ends than they are at the root. And then there's for like cargo jets that have really heavy, they usually have this. Fighter jets are common to see that. So that's what's called an anhedral angle. So if everyone hears that, you're going to know why. And why am I bringing up this right now? Because we're going to talk about the idea of an anhedral angle in the hip. So the first time I ever saw this was from P&D Botics, and this is their Anabot. And it was kind of intriguing. It's like, okay, why did they go ahead and do that? I wonder why that's there. And it's a really strong anhedral. I mean, it looks like it's about 45 degrees. And it's like, okay, I mean, they just didn't put a little slight angle and they decided to go all out. And why is it? And there's some things that look kind of cool because it looks like this angle intersects right here where their waist rotation is. And there's a lot of, let's say, things that seem very elegant about it. But why did they choose that? And then I looked at this and I superimposed this over human pelvis. And you'll see if we, and I think I have to just go down for a second here to remind us a little bit of human anatomy. You have the femur and what's called the femoral neck here, as well as the head that fits inside the acetabulum, which is basically the cup that grabs the hip. And you'll see that this neck makes, about a 45-degree angle. And it's very tempting. When you look at this, you would assume, oh, the leg must rotate about that, right? Because it looks like an axle. This is a ball. Everything is happening up in the ball. And you see that neck that's coming out. You would think, we must rotate about that. That's what it just seems like to me. And you think of that because if you have like a tripod for your camera, there's something that sticks out that you put it on and you tend to move that and then rotate about. So it just seems like it must be there. That's it's an artifact. It's really not there. It doesn't matter. It's completely arbitrary, the direction of the femoral neck. Part of it's there because um, evolution has decided that's the best strategy to get that offset that you want to have in there and get the loading and everything right. But we do not rotate about that. We more like actually rotate about these three axes here than that. So they decided we're actually going to rotate about that. And I think they they maybe were inspired from that, but did it for the wrong reasons. I'll show you kind of why in the problems that this kind of causes. And that is, I took our Decimate, remember our Decimate robot, and I put in a 45-degree anhedral angle here. And we can go ahead and look at what happens when I just rotate the F actuator. Okay. So when that happens, look what happens to my leg. It has to stay in this plane. The rotational axis is in that plane. So everything rotates from that plane. And you'll see that everything gets really screwy as far as that movement. That means I have to compensate for that by giving it a little bit of actuation. So at some point here, I'm going to say, all right, what happens if I decide to go in here and actually actuate this thing? With the actuator, and that kind of straightens it out. But then I need to get rotation in there. So that means I have to get all three axes coordinated just to get my leg to swing straight forward. And you see, then if once I put those things in, it gets even wackier if I move that. So that means all three of those have to work in order to move in the plane. So why not just go ahead and build it so, like this with no anhedral angle, so it kind of swings in there.
And what is benefit with it? Making this angle like that.
I If there was a huge benefit, you would see a lot of people doing it of that level. At first I thought it might have something to do with packaging or other reasons to putting in there. Um, there it's going to cause more problems. I could see an engineering design meeting where someone says, "Hey, the problem we have with the flexure is that it has to carry that whole load of the rotational inertia of the leg, and the rotational inertia of this leg about this axis, because you see this mass that's hanging out here. If you take that axis here and you were to calculate the distance from here to the end of your foot, it's a shorter lever arm there than it is this way. So it's about 70% shorter. And so you would say, that means I only need to have 70% of the torque to be able to get that. And in order to straighten it out, all I could do is then use the torque of the abductors. So the idea is, like, you think about, well, what I can do is I can combine the torques of both these motors. So rather than having to have one big motor, somehow I can mysteriously take two of these motors and combine their torques to give you the motion you want in it. That could be the argument that someone made in the design meeting, and everyone went for it. And it's like, I don't know that I buy that. I, I, re- so, so I'm not even sure I would have made it, because a lot of people are going to probably say in the comments, "Man, that is such a stupid observation. There's no way that was the reason." But it's the best you can come up with. And again, it's like I almost don't believe that that would be a good strategy. I just don't see the point in it. All right, so if that's not the point, then what's going on here? Okay, so here is. Oops, why did I slip back? Okay, here's Engine AI. And if you look at Engine AI, I think they have a little bit of an anhedral angle. I mean, not like what P&D Robotics has, but it looks like I think they have one. If we look at the G1 from Unitree, if you look here, do you think they have an anhedral angle?
To some extent, yes, I see the slippery, the
It, it,
timbering
it,
in the
it,
walls.
it looks it looks like it, and I thought they did. That is an optical illusion. It's because this cover they put here. I mean, you're seeing that angle on the cover there, and it's tricking your eye. And they also have like a little angle going on here on the how the yoke kind of connects that. But when they actually have the waist cover off, you look at those two actuators, you're like, well, wait a minute. No, they are horizontal. And I thought for sure there was, until I like started to do the research of that. And I was like, oh, I was wrong. It's like, that's a trick. That's not actually that way. Yeah. Now you come over to Boston Dynamics New Atlas, and that is not an optical illusion. It really does rotate there. Okay. So they have a slight anhedral angle. It's not as strong as P&D Botics, so it might be okay. It may have a little bit to do with packaging density. Maybe by you get the extent, maybe just opens up a little bit. I'm not quite sure the overall advantage of it. It could also be that Boston Dynamics has really leaned into this idea of um, really wide ranges of motion, of being able to turn themselves inside out. And it may be that when they kind of turn around, they found that there was some advantage to having this down a little bit, because their legs can just kind of go around the other way. There, there may be. I'm not 100% sure that would be the argument, but They wanted to come up with something that was really open that allowed them to have this inversion kind of capability when they're moving around. So they have a slight one. I don't think a slight anhedral angle is necessarily a bad thing. You know, you will need a little bit of abduction and rotations are going on, but they're minor. It's just that I think P&D Botics probably overdid it by going that far because we can see how much those things kind of swing out. And again, it may be, maybe they really are onto something there as far as the torque requirements, but I don't think so. I think it means that overall you're you're putting more wear and tear on all your actuators, not just one. Now they're all having to work double duty. So we've only seen, Optimist is done the ARF, and has anyone done ARF right? And I get this comment on my it's all in the hips from a student in China where this is a design for his bot. And at first I thought it was like the original Atlas bot, and it's not, but it uses kind of a similar actuation strategy. And that Boston Dynamics kind of got it right. And the reason is that if you look right in here, you'll see there's like a rotational axis here, and then there's the articulation axis or the abduction axis right here, and then the flexure is right in there. Now, these are both hydraulic robots, so it's a little bit easier from a packaging standpoint to be able to get that to work. And Boston Dynamics sort of did the same thing, is that they have, basically the A and the R going on up here. And actually this might be more of like an RAF. And for the most part, when you package your joint like that, whether it's ARF or RAF, it doesn't matter. It's almost the same. The main thing is that you get the flexion out at the end, out there, and you see it's up high. It's right in line where it needs to be. And so Boston Dynamics kind of got it right. The only thing is that this offset, um, their offset may be all right because don't look at what's well. Yeah, it might be from the standpoint of the femur and where the rotation is happening. It's kind of a bit inboard. So maybe shortening that distance right there might be a little bit better. But the idea is that you have this shaft, and on the end of that shaft is basically where you put your actuator in there. And that's really close. So that gets us much closer to the human anatomy, even though the femoral neck, if you want to call it that, is horizontal rather than 45. It doesn't matter. It's because again, that's kind of deceiving you on what is the best way to proceed. Uh, okay, so again, we can kind of see that this is how Unitree did it, and getting very close to that kind of motion. And now I've got maybe a little bit of bonus that I want to go into here for a second of something that came up there. But before we do that, do you have any thoughts or any observations?
First of all, I want to say thank you. I think the research and the observation you have been doing so far in this humanoid robotic series, it's just remarkable. I appreciate the effort and the time to come up with such unique analysis. And I'm not sure if you shared the feedback. I think people appreciate your unique insights in that so far
Yeah,
in the
yeah,
research.
and the thing to remember is that the whole system has to be designed. You just don't do the hip and then do the waist. You're really going to look at them as something that works together. That's going to impact the way you walk. So when you're making those decisions about walking, like, do I want my shoulders going back and forth? And if I don't, how do I compensate for that? And if that's something I'm going to put in my RL, that means however I walk is going to be a little bit different on how I might have to bend my knees more or something like that to make sure my foot doesn't kick the ground when I go around, as opposed to doing this hip sway back and forth. So these are all decisions that are going to impact it. So again, the anatomy is going to drive the results of the RL a lot, which is why Chris is exactly right. His point is like, isn't necessarily optimal. And I think it's okay if, so long as you aren't too rigid about it. We went back to the gait analysis. And one of the things we could do with that gait analysis is say that we're going to put that into the RL and we are going to actually force feed it. Now, the way reinforcement learning works is it's a reward function. So you basically give it a candy bar or lollipop every time it does something good, and you slap it on the wrist when it does something bad. And over time, it does what is closer to what you want to be the right behavior. In some cases, you might again prime the pump where you give it some sort of rules that it already has to obey, and then when it does kind of well, like chess, like it's like let's give it the rules of chess, okay, and then it learns to play from there. Or you go ahead and say, we're not even going to give it the rules. Basically, what we're going to do is that when it makes a legal rule a move, we're going to slap its wrist. So it doesn't actually know the rules. Same thing seems to be happening with full self driving right now. I'm not sure if it understands you're supposed to stop at a stop sign or if it just stops at a stop sign because that's what people do. Because there's a lot of this behavior that seems to be more or less like it's emulating what people are doing without actually knowing what the driving rules are. And that can have both good and bad consequences. Because sometimes strictly obeying the law when you're driving can be fatal. There, there are times that it's like, oh, okay, it's more of a suggestion, but we sort of know what the dynamics are drive, and that's sort of the same thing that can be happening with the walking. Is that you want to give it, let's say, some suggestions, but back off and not say, oh, wait a minute, from our gait analysis, you need more dorsiflexion here when you do this. Like, maybe not. It doesn't have a toe box. Okay. It doesn't have a lot of these other things. So we need to do something there to make sure it comes up with what is actually the optimal strategy. But again, we don't want it to do crab walking and stuff like that through the house. We want it to be actually erect when it's walking. Yeah.
Maybe a quick question because you mentioned the figure post of the like Reddit Coke. He said the zero shot in the humanoid, so all of them have the
Yeah.
same walk.
Yeah. Yeah. Yeah.
Do
Yeah.
you think there could be changes needed in the foot design when you show the Tesla, for example, movement? I'm not sure why they make this decision based on reinforced learning. Is it because it's linear actuation? Does it contribute to that the way of
It
the
could be.
design?
Yes. Yeah. You got a different strategy in the ankle. You have and the thing with the ankle is they've got the pretty much the two linear actuators that go down there that could maybe give it a kind of sideways push on there. Um, and the hip flexure is a lot lower. The way everything is actuated, so the the resulting walk that you get out of those two, I would expect they're going to be different because they are just kinematically so different. And again, it's very hard when you try to line it up with the true human gait that we could be really critical and say, "Ah, look what it's doing. It's walking kind of pigeon-toed there. Is this that's kind of weird. Why is it moving? You're gonna get an ACL tear if you keep doing that, or chondromalacia, or some other kind of issue with your knee if you do that." It's like, no, he's not. Now, it could depending upon the kind of actuator you have there. At the knee, they have a hinge joint that's there, and that hinge joint can take all kinds of loading, way more loading than your knee can take. It's like football players are constantly, being very careful about when they get struck there. If they take something, that could be catastrophic with the knee. Optos could probably take a little bit more. Now, to actually build an actuator right in there, and that's your hip joint, that actuator has to not only provide a lot of torque, it has to take a lot of off-axis kind of loading that could affect the bearing surfaces. So it may be that if you put that in your RL, say, look, we don't want any twisting in the knee. We have to reduce the loading on that. We only want axial loading or any off axial stuff. That's going to be one kind of walking strategy. Whereas if you get something that's a bit more hardy down there, you might just say, oh, we could do this weird kind of little twisty thing there, and that's not going to affect anything. So I'm assuming, that's behavior that may have come out, and they may be examining that, and then also asking themselves, is that actually good or is that bad, and kind of going through it because it doesn't line up with and I've encouraged everyone here that after looking at that, this is what physiologists do, or sorry, what basically physical therapists do. And that they will put you on a treadmill and they'll sit there and they'll look at it. They might put a camera and they do a gait analysis and everything else to find out what's wrong and what exercise you need. They should all be doing it. You're a humanoid bot company, your startup. Either talk to your physical therapist if you have one, and either pay them or give them equity in your company and bring them on in and look at this stuff, or go to some university where they have some physical therapy lab there and just find some grad students and say, hey, you're great to help me out my new startup here, and they can look at that and give you suggestions. But again, you have to remember, we're not talking about analyzing human, but at least the framework should be about the same. And then you begin to realize, and I have a feeling a lot of doctors and physical therapists are used to the fact that you've got a person who may have something wrong with their foot, that they don't have the flexion in the toe box anymore. And they may say, well, based on that, this is how we expect them to walk. And then you can kind of compare it with the robot and say, yeah, that gait's acceptable. So we are going to see differences coming out, no doubt about it.
Maybe a quick question. Do you think because when you lay the two figures from each humanoid company with the human, do you think they consider like some expert in their design, like from physical survey, for example, to tell them that's how you should have the axis of the head, for example. You know what I mean? This guy.
Yeah, I mean, part of it came down to an engineering problem is that the FAR design lends itself as being really nice for packaging because the last axis, the R, you can package in your hamstring. It fits neatly in there, and it just doesn't get in the way. The problem is because that rotation is there, it's now outboard rather than inboard where it should be. It's down the femur, and we don't actually rotate down the femur. It's a little bit different. So that causes our gait to be a little bit different because of where that point. So what that means is you haven't lined that axis up right. So it's very neat from a packaging standpoint, but it may be a little bit wrong from the physiology standpoint. Um, and like I say, with the exception of Unitree, which is got like R as the first axis, they're able to put it wherever they want. Everyone else is doing it down the femur just because it seemed like, the best place, the logical place to put it from a design standpoint. Um, and a lot of people working there, they have training in biomechanics. They know quite a bit about it. They may not necessarily be MDs or physical therapists, but they know enough about it, and they're well aware that the way human anatomy works and that the musculature and how it's radically different. But they're kind of looking at it as a standpoint is like we just got to get these rotations, these movements, and hope that it's there. And again, kind of back to your point of like the zero shot going on there. The zero shot is working for figure only because all their bots are identical, close to identical. We've talked about the fact that even in the sim to real, they put basically noise, a certain amount of perturbations on the performance of all the actuators. So all the actuators are not identical. They have kind of a range of functionality because that's the expectation is that each actuator in reality is going to be a little bit different. So they have enough with that range that when they go to their bots, the bots are fine. And they may have like a calibration phase that once it goes into the bot, they may walk it a little bit to find out what the nuances and differences are by knowing like this is what the actual actuation capabilities are of this bot. But the thing is, that's going to vary during the day, and we're pretty good at that. We get up in the morning and maybe we don't feel as full of pep as we do later in the day after we've had a good meal or stretched or something like that. It's gonna be the same thing in the bots. Is that when they first start out, they're going to be in a cool state, and then they're going to be moving a bit, and then they're going to start heating up. And so there's going to be changes in there that they're going to have to adapt to anyway. So, but that's important to the zeros. So whatever solution that figure comes up with, you cannot translate it to Optimus. It probably would not be the optimal because it's a completely different strategy. And again, if figure comes out with a 6 foot robot instead of a 5'6" robot, it won't be quite the same. It might be close, but they would have to put it back into RL. And that's the whole idea. The thing is the RL seems to be able to give results pretty quick. Not instantaneously, but as type of thing. It's not like, oh, we have to run this thing for a year to get any results. No, they can go through and that maybe in a couple of days be able to get some sort of results and upload it and try it again.
Maybe for the sensing, I think when there are RL camo decision like for Optimus, do you think which joint is very critical for them to make this decision of movement? Like the first maybe essential joint to make sure the decision is made
Yeah, I
toward the
mean, the most important joint is obviously flexion for walking. Your The argument could be which is the second most, and I still haven't got my ranking post out there yet. That I'm sort of torn between whether abduction or rotation is number two. Ab- ab- the abductors seem to be very important for kind of balance and stance. If And then we're just talking about walking. If you want to be doing squatting and other things, so you got to remember when you're looking at these things, a lot of times people think the task is just walking. It's a little bit more than that. So when you want to squat down and do a few other things, you need to have the abduction because your knees kind of have to spread out. And then if you're carrying a heavy load, you need to. But rotation is very important to change the direction. Without it, you can't change the direction. So when it comes to walking, I mean, there's two things. First, being able to walk, and then being able to turn. And so it's like number one is being able to get the movement, and then second, being able to turn efficiently. And of course, but other people say, yeah, but the most important part of walking is not falling down, and you need the abductors. So I'm not really saying that you would remove any one of those axes. They all have to be there. And I think there were some people that may have attempted at first to say, oh, we don't need the rotation. Abduction would definitely need. We're not quite sure you need rotation. And they probably quickly realized, oh, wait a minute, that walk, that turning is very important. So you have not seen any without rotation. It's there. And it may have been, like I say, initially, oh, boss, do we really need that in there? And then they quickly said, what about turning? So they are very important. But then as you go down the list, you can start to argue what is the importance of some of these. Like I said, you don't really need the knee for walking. You can walk stiff kneed, but the knee is really good for being able to squat and do a lot of other things. It's very important, and it also does make your stride more efficient and everything else. So it's not like you want a bot without a knee. As you said, I'm saying it's not as important as the first three dreads, but it's up there. I mean, it's clearly number four.
Okay, I think we should talk about that in detail for upcoming episode.
Yeah.
Yeah, and you shared the bonus about no
Yeah,
the drum.
so this morning I've kind of known of this company for a while, but I haven't really
Can you
tracked
share
this
explain?
as
Yeah,
closely as I should. And
actually, I interviewed you, and his name is like David. I remember, but it was like
yes,
4 years.
yes, yes. And it would be worth actually setting up another interview with them because they've been more, I wouldn't say they've been in stealth mode, but they've been kind of quiet. It's always the Chinese against the North Americans. And we kind of forget that, the EU does have some candidates that are in there. And I've been kind of aware of them, but I haven't looked at as closely as possible. And today, when I went through it, it was like, wow, they are interesting. Okay, so this is Neura with their for NE1. It's actually pronounced for anyone, bot. And this is, and what kind of intrigued me when I looked at it is there anything interesting about what you just see from this image? Now, this is actually a CGI image, but it is very close to the real bot. And there was two things that kind of jumped out at me. What did you, in anything that you notice?
I think the hand, the elbow jaw is quite high, a little bit different. The elbow, and I also think the hip is strange. It's like
Yeah, yeah, yeah. So the first thing was, I was like, oh, darn it, just like 1X, we have no idea what the hip is. And so I was like, oh, what kind of hip is it? Is it a far hip? What is it? Are they using the same thing? But it's so neatly covered up there, we can't tell. I wasn't sure if they even have a waist or not. I mean, they could, but the other thing is like, wait a minute, that wrist, that is such a compact wrist. No way. No, this is just CGI. But the thing that really made me go crazy is that I said, wait a minute, they may not have 3 degrees of freedom up here. They might have like an AF or it's you know uh, and the because look right down here. You see that line right there? If I'm not mistaken, that means they have rotation there. It looks to me like they're rotating below the knee. Like nobody rotates below the. You remember I said that's toxic. You don't need that. Why is that there? And if you're putting it there, it means you don't need the rotation up here. So that's what I'm thinking. Oh, they probably had. So maybe that's a. So these are like the conclude. It's like conclusions I jumped to. Okay, so I was jumping to conclusions here. So I've got to sort this thing out and kind of what's going on because I it was a head scratcher. And again, I'm wondering, oh, this wrist. There's no way they have 3 degrees of freedom here. They might be using the redundancy that you have up here in the shoulder for that, so they could get away with having such a, a wrist that look at that. That is a very slender wrist. It's the most slender that we've seen. It's like, all right, how are they pulling this off? So,
what they
here's
looking.
like
Do you
another
think
image.
using abduction flexion in the hip and this rotation beneath the knee?
Oh, I'm solving. Don't worry. Don't worry. We're going to uncover the mystery because it's great. It's great. So, looking here is another CGI to get an idea that their speed is not that impressive. 3 kilometers per hour is not 3 miles per hour. Okay, it's not quite 2 miles per hour. If they could do that, and it's just like a little bit below of where we would like it to be for being able to do useful work in the factory. So I don't know if that's their target or if they can actually do that. But again, looking here, we can't get enough about what's going down here in the legs. It's a computer rendering. But when I look here, I'm not seeing anything that indicates rotation about the leg. I mean, you could see this here. That's just a cover plate coming off. It's like between here and there, you see nothing that would indicate that the leg can rotate. So they must be doing it all down there. So Still a six off leg. It's just that they reorganize everything from one leg. So it's okay. It might be different. We could see it. The wrist rotates here, but we're not quite sure what's going on there. Again, from this, we can't really glean anything, and this is not conclusive evidence of anything yet. So I found this image, and like one was like, "Oh, cool! I can see something else." So sure enough, they have a waist. You can see the waist in here, and you can see the linear actuators that are in here, and you can see the Cartan joint that's here, and you can see the rotation. So they have a 3 degree of freedom waist here. So they would have what's a ZXY, a Z dash XY waist is what's there. I can't see enough of what's going on here in the hip because the table gets in the way. Like, and I'm not quite sure what Matthew Broderick is doing in the image. So, okay, so we got this image here. Are there any better images? The other thing we could see is like, look, they got a camera suite right down here. I assume there's one up in the head. We can kind of see that. Um, there was this line. It's like, I can't believe they showed it without its soft covering. And you can to see something. And it's very hard to tease out. Very, very hard to tease out. And so again, we get a much better view of the waist up here, but you can see here, um, we can see what are the rotary actuators. So this is their R, and you'll see it has an angle. I'm not sure whether that's a kind of an angle, yeah. Um, and because but it's the rotary axis, not the flexure, so it's really weird. So you get the rotation coming down here, and you have this thing here, which is like it looks like a huge yoke, and I'm not quite sure. It's so big, it's suggestive that that point there must be where the abduction happens. And you would think because it's so big that there's probably a rotary actuator right in there. But I think you would be wrong because I'm seeing these connecting rods over there. And I think this is just a big cardan joint that we can't see enough. And something is going on down here for the flexion. So I'm not getting enough to completely tease out the mechanism, but I think it's sort of what we've already seen in Apollo, and we definitely saw in the G-Peng iron robot, that they have two linear actuators in here to do the trick of flexion and abduction. That's what they're now, this big massive thing here, this looks like they have a huge servo in there. My suspicion is that's for the knee. That was my first suspicion, and it looks like I'm right. The other thing is we're gonna see some interesting things here about the wrists that are gonna come through. So they're doing something here, and again, I'm not getting a clear enough impression, but however they did it, it is very
So it's
compact,
nice.
very oh, it's this is German engineering, okay? And so they're based just south of Stuttgart, and I think it's Metzlingen, and it's known as that's where the Hugo Boss factory outlet is. So if if you're looking for it's the Hugo Boss up there, yes.
This is rough, right?
Uh, okay, I think it is. R, it's yes, it's the RAF that we've talked about, R dash AF, which is what Apollo and one axis. So if I was to put it on the graph, it would be over there. So it's a kind of RAF, but it's got the parallel mechanism. It's not RAF, R dash A dash F, but it's definitely R dash AF. And that's so that's a pretty interesting. I'm hoping to find more evidence of exactly that, but it seems to be very compact to what we've seen of the others. But they seem to be using a lot of linear actuators that we can kind of see. So continuing on through here, a glimpse at the hand. Couldn't see very much in the hand, but it looks to me like they have only they drop one of the IP joints. So you have the pip, but you don't have the dip. So out here they have it kind of pre-rotated there. The question is whether they're using tendons or not. I think I know the answer to that, but we'll get to it a little bit further on. But here is also like a quick glimpse of the interior of the torso. And you see right here, this is a linear actuator that goes all the way down to the waist. So that's like, man, that's one big actuator. so, so that thing's got a lot of heft, and they got probably one on the other side. First, I wasn't sure if they were using that for something else, but it looks like they have whoops rotary actuators up here for the shoulder. So I don't think it has any to show. But then I noticed right here, oh, there's a camera suite right on the side as well. So they have this camera here, they have that camera here. They seem to have a lot of cameras pointing right. And of course, we can see it here. They've got, downward facing camera. They have cameras over here on the left and right that we get an idea. Now, this is the one part that I guess surprised me. And that is notice that the shoulder has an anhedral angle. We haven't got into shoulders yet, but we're going to see that this angle is a very important angle, and that I think they're the only one I've seen going anhedral. They should be going dihedral. A lot of shoulders are actually neutral; they come straight across, and this comes down to singularities. And what that means is that if you start working up with your arm around here, you're going to have these singularity issues of things flipping around. It doesn't mean you can't work up high. It's just that you have to get yourself around that singularity some way. And it means that it would almost prefer to always work low below that level. And then once you get up around that plane, it's a bit tricky. So it's not the choice I would have made. And that's one of those things that I would love to talk to one of their engineers, perhaps David, to find out. It's like, oh, okay, why that? Why didn't you go the other way with it? And it may be that they just feel that, oh, they can conquer it with software. There is a way to get around there that it may or may not be important. And it may be that it gives them almost a more human appearance, you could say, as far as like the shoulder blades and everything else that are coming on down. I'm not sure how big the battery pack is, because with all the stuff that was in that torso, I'm not sure there's any room for batteries. Okay. This here was see. Oh, there's a back camera too, so we can see the side camera. So they've got camera. I think all the others do. The others is more or less just like more camera in the head. The original Tesla design was putting it in there, and then they kind of scale back and just kind of put one in the head, because every one of these things requires compute. So at first, the feeling was that you would just have your bot littered with sensors all over the place, and you put it in places where they wouldn't be blocked. And most everyone is saying no, no, we'll just go with one, because that's CP. There's a lot of compute and synthesizing all these images and stuff like that. So I don't see, they probably have their own reason. And it looks like, it's kind of I think an off the shelf kind of sensor that's very common in a lot of mobile robots. So, and the other thing you point out with this company is that they've been around since 2019, and they didn't start building humanoid bots. They started building mobile robots and cobots. They have tons of experience in the cobotic field. They have cobots that are working in factories today, and cobots are designed to be around humans and not hurt them. And they know a lot about actuators and stuff like that. So they are probably like the only, pure robot company that decided to start building a humanoid bot. I'm still waiting for, the ADBs, the Kukas, and the Fanics of the world to get involved in the humanoid bot space, because they're coming from that. And it may be they're coming from too much of an industrial robot space and not a cobot space. So this is like a natural pivot. Is like, if you have a lot of expertise in that area already, I think they can do it. So again, they work a lot in mobile robots. They know a lot about navigation, and so that's probably why they're comfortable with these suites and believe that they can handle it. So we can get a little bit of an idea of what it looks like there, and some more. Now here you can just see the hand. You see the clasp. I put this in here because you can see how the hand is closed there, because of one IP joint there. It doesn't curl all the way around the way we would be
It
used to.
doesn't seem a good hand at
Then
all. This is not a good hand.
it's an okay hand, considering that I, there's so much to a humanoid bot. You can't get it all right, and it's not bad for starters. And it seems like they're doing a lot of tasks with it already that may be sufficient. The other thing I noticed is that it really stands tall. It stands really quite tall. It's about 5'11", and for a German humanoid bot company, I'm not surprised, because the German population tends to be demographically a little bit taller, like the average human, and so it would fit in a bit more, being closer to probably what is the average male uh, in Germany. And just looking at it, it's like, oh wow, look, its knees are straight, absolutely straight here. So that's rather interesting to notice. Now this I love. Okay, this, remember I was talking about the knee. I wasn't quite sure what was going on at the knee. I was pretty sure that this big actuator you see backing here actuates the knee. And here you see this here and that here. that I believe are the anchor points for the two actuators that we might be able to see a little bit from here that go up and do the flexion and the actuation. Now, I'm really surprised at the size of the knee one because I would think the flexion would be more important. And I'm not sure that even with the two of those, you can get as much oomph out of those as you would with this. I could be wrong, but just look at the grandiosity and size of that thing. And this is just beautiful. You're going to love this. Yeah. So let's look at that. You can see it rotating. You
I
see
just
it?
want to understand. You say this is barrel mechanism to do the flexion and abduction. So what does the rotation is doing here?
Well, this here is what you, is this is the knee joint. And you're seeing this is the linear actuator. It's a really long actuator. It's pretty big. And this is the roller screw. So right there, you can see the roller screw coming out, and you can see the actuator actually spinning. So it's spinning and is causing that linkage to extend out, and that's what's causing the knee to move. Okay, so basically, it's retracting at this point. It's pulling that whole thing in. So it's rotation such that that length is getting shorter and shorter, and you can see where that knee mechanism is connected right there. So you can see how that's so it looks like I mean, that's the whole thing is all motors spin. And a linear actuator is taking rotary motion and converting it into linear motion. And that's how yeah, and the way it works is it works just like a screw. So if you put a screw in a board and then you start to take a screwdriver and spin it, as you're rotating that screw, you're going to notice it translates forward till it goes into the wall. And then if you counter rotate it, you'll notice it comes out. And because that thread allows it to move in and then to come back out. And that's exactly what's going on here is that in order, and the reason why the thing is so long is because you have this very long rod that's inside of there that has the thread along there, which is the screw, and it's a roller screw. Usually have ball bearings along there to reduce the friction. And think of the motor as basically being a nut on a somewhere. Oh, yeah, here we go. Ooh, props. Okay. I've got the kind of a prop here is that you see if I spin my nut, you see how the nut moves along there. But if I somehow have the nut spin this way, but keep it in the same position, it's going to cause this bolt to move, right? So as this nut is spinning around, and if I'm not, instead of turning uh, yeah, I think you get the idea. Is that spinning motor is going to end up causing that rod to extend out, that little linkage mechanism, which is then connected here to the knee, which makes it move. And it has to be very long because they need to have a lot of travel. And if your motor is very short, then that means you don't have much travel before this thing falls off of the nut. And then so you need to make sure it's very long so that when you retract this all the way in, right? If I retract it all the way in, I've got to have my actuator be
I
like
understand that
to get
just
it in there.
quickly. The one the barrel actuators for the flexion abduction is not related to this part as well.
Correct. So it looks like they're in here somewhere. So what I think they have is they've got a big motor like this, and then they have two smaller ones up here. So they get a big one, and then somewhere up there they've managed to fit it, and we can barely see like there's something up here, but we're not getting enough of a view. And that there is probably the anchor points for the ends of those two. And those anchor points are going to have to be some kind of Heim joint there or a spherical joint because the movement of those things, I think, goes in a couple different directions. But again, if you look at the overall packaging that's in there, and again, it's a little bit like a stormtrooper, these these plastic external parts here that kind of cover it up. And, as we go along and look at it, that normally is covered with fabric. And right here, for some reason, the fabric rolled up, and we get to see a little bit of what's going on. Again, these control rods are kind of going up to help with the flexion. So they may not have worked out exactly how to cover this whole mechanism yet without always slide.
But it
It's got
seems
to
what
be
I understood
complicated.
from you, it seems much better than what we haven't compared to other humanoids.
Yeah, yeah. Well, there's some interest. Yeah, from the way they've done that, seems to be really good. Now, this is a 3-bar mechanism they have here, as opposed to like the Herkins joint that we talked about that Optimus is using and iron. And maybe that's why it has such a big actuator is because you have kind of these deadlock situations you have to be careful of. That as you get near 0 degrees or 180 degrees, you lose all mechanical advantage. And depending on your range of motion. So it may be that there's some point for you to really need like a lot of force to be able to get the knee to kind of move the way they want. That could be the only reason because I don't see why the actuator diameter has to be so. I understand why it has to be long, but I don't quite see why the diameter has to be so big unless they really need to come up with a lot of power. But again, looking up here at the wrist, like they almost don't exist. You're looking at that, it's like that is just such a compact kind of wrist mechanism in there. It's amazing. Um, now, okay. Oh, that was like I didn't clip very well at the very end there. All right. So now let's take a look at the wrist. And so I was able to grab two images that they had in there of the wrist. And you can see right here, here are the two linkages that actually cause the move, just like in Apollo, just like in Optimus. That same idea that you have a cardan joint down here, what I think is a cardan joint, and they've got two linear actuators, much smaller linear actuators that make these control rods go up and down. And we're going to see a video of this in a second, but these are kind of two glimpses. Um, Now, one of the things they did, so at first I thought, maybe they got rid of the wrist yaw, right? Because I wasn't sure how they made it so thin unless they did this actuation strategy. And you'll see that they've decided that for the pitch, they're not going to have like a, a huge range on the pitch. They got a pitch that emulates the human. So you see kind of the back direction doesn't go very far. Well, my hand really only goes this far back, but down it goes really far. And that's why you can see this cutaway here. It allows them to pitch a lot, which is rotating about this. The other thing that's interesting is that I think Optimus and Apollo have their card joint more in the center here, and they intentionally offset it there. And that offset makes sense if you want to have a range of motion which is non-symmetrical, that you're favoring one side over another. And that's sort of anatomically correct. That's why they put it there. So you can see this is where the pitch axis is. And I think they have like in here another joint which allows them to get the yawing motion that's going on in there. The other thing I want you to see is that this kind of mechanism just is very easy for your cabling. You don't need any external cabling. You see it just smoothly runs right into it because it is opened up. There's the other thing that amazes me is like I'm only seeing okay, this yellow wire, I'm not sure what it's doing. It kind of goes up and back around like that, but you got well, it looks like just three wires heading into the hand. Yeah, I'm expecting you like more. Maybe there are some other cables around. It was like, oh, there's not a whole lot of cabling left after that. Just goes right on in there for the hand. So they don't need to route very much, and you see they got plenty of space to be able to route any sort of cabling that you would need below that point. And right here we can see the actual point of where these connect onto the wrist to be able to give that lever arm and a much nicer view of it there. Again, that's kind of it has to be a Heim joint of some sort there for that mechanism to work correctly. Now, looking at this, my impression is like, okay, they probably don't have a whole lot of movement in yaw, but we will see. So now you can see how it works. So is that now pretty clear, at least for the pitch? You'll see that rod pushes down, rotates about there, and that's how you get your pitch. They're not showing the yaw that's in there, but I think we're going to see something in a second here. Okay, here's again a close up of the hand. Again, that wrist is just crazy thin. It's just so slender, and even the forearm is not very big. This is much more slender than the Optimus forearm, and they've managed to go ahead and fit those things in there. Another little view that we can see the opening in there, and we can also see a little bit of what the hand looks like. Most of the images that they showed of the hand were very blurry, so good, really good detail in a lot of them. Uh, and so here again, it looks like they've got probably different versions of the hand. This one's white, but this one I put in there. It says, "Oh, look, they do have decent yaw." So that was like more yaw out of that wrist than I expected. So I was finally able to get an image catching it in kind of the yawing motion there, which looks like might have something to do with. I'm not sure if that's no, that's probably not what the joint is. I don't think I think the joint that might actually be data. that they plug into. But we can see where the IP joints are. We can't really tell whether it's tendon based or not at this point. Again, this really blurry image of the hand where we can see. Yeah, so if you look at that, you'll see something going through here that is suggestive of like a tendon. The question is it really a tendon? And I think in these pictures we get to see a little bit more, so we can see how the thumb is done. We can see kind of these little points here, and that usually is an indicator they probably have a linkage that's built in there. And I could start to see a little bit here and then I think the next image, it's a bit more in focus. Yeah, you see that there? That's a metal rod that comes right. So they are using a linkage mechanism for the control the movement of the fingers. Now I don't think they have the abduction of the fingers. I think they only have the flexion extension. But I'm pretty sure we can say this is not tendon based. This is purely mechanical on their hand, what they're doing. And again, it only has one IP joint instead of both. So that's which may be good. I mean, we'll have to find out how much you can actually do with a hand of that kind of complexity or not. All right. Now, as far as walking, they did not really show it ever walking. It's always in a standing position. This is a clip from a video they had where they quote showed it walking, but at like superhuman speeds. I mean, it just was like the time lapse was crazy. So it was just a blur going through. So it was like watching the flash just, and this was like only one incident that I could like stop the frame to see where it was in the movement. And so if that's their moving policy, walking policy, it looks like its legs are still bent, but it could be that this is the posture it takes to pick that thing up because the chances are I would be bending my knee to get down to that and not necessarily standing up straight. So it's hard to tell if it is able to keep its knees straight when walking. It can definitely be very straight when standing. We've seen that. So it was hard to tell. The main thing I wanted to figure out is like what's going down in the ankles. I don't, and this is like the only picture I've got of the feet and the ankles. And I tried to blow it up as best as possible. And I have a feeling since they've been,
It's quite strange foot.
yeah, it's hard to tell, but because they're leaning so much in with these linear actuators in many places in the wrist, in the waist, up here, I'm willing to bet that it's the same strategy on your cardan joint with two linear actuators for that Mimo kind of multi in, multi out parallel actuation. I'm pretty sure that's what they're doing, but again, it's too grainy at this point for me to say conclusively. But uh, yeah, there's never any guarantees, but let's say I'm 99% sure that that's exactly how it's actuated down there. And yeah, that's it. That's my- that's a separate episode right there, I think. But
I think we should have the CEO, Neura on the podcast.
it's fascinating. I mean, from the mechanical standpoint, it really is standing out. Is that they've done a lot of very interesting things. Um, the it's just so slender in so many places, and the actuation strategy in the hip uh, looks interesting. Um, how they did it, it seems to have been simplified a little bit from the others. So it's a different pod. It's one of those with a mix of linear and I'd sort of talk about the different schools of thought out there as far as actuation strategy. That you have one group that I say is up at the North Pole, which is just all rotational, and then at the polar opposite, down the South Pole, those that are doing linear actuation, and that's Apollo, Keeping, uh, with iron, and then you have those, the one that at the equator, which is Optimus, and now it looks like it's kind of been joined by for anyone that it's also has a mix of the two in there that seems to be similar to the Optimus strategy is as well. So they're definitely worth looking. I, yeah, yeah. They're I mean, the first thing I need to apologize for not having, like, looked at them sooner when I was doing my other analyses out there where they are because, now we are seeing there's at least one other that's kind of Well, kind of an R strategy that's stayed in there. So their their hip strategy is a little bit different. So the numbers have changed a little bit, and I think we can kind of call them a major player at this point. Looks like they have good funding that they raised. I think 120 million euros. They have an order book of about a billion. Um, and now I don't know if that order book of a billion is like just for humanoids or for like all their bots. So it looks like they already have cash flow because they have this other line of robots that probably helps keep the organization going. I think 300 employees or something like that. So they're kind of past that startup phase. Yeah, the only question is what is their AI strategy, and it seems to be that they're working with NVIDIA and Isaacs and stuff like that. Because one of the videos that went out there, I think, was showing their connection with Omniverse. They also had something showing the Omniverse where there's some images that I didn't realize was actually like out of Omniverse, and then they showed the real. Like, aha, okay, I was able to see a slight difference in there. So they clearly, they're using NVIDIA to help them out a lot of it. Just not sure where they get the compute from and what other neural nets that they're using or how much is homegrown. But from the mechanics, I mean, it's your typical kind of solid German engineering that it's compact. It's remarkably compact. You could see these memes. People are showing like what a German robot would look like, and it would just look like it. I have like these really weird buttons and be really bulky and stuff like that. But you see in this case, they've done a really good job on the packaging. That's so
I see your eyes lit up when you say
yeah,
that German
yeah. I mean,
engineering.
there's reasons why German exports as much stuff as they do, and their stuff ain't cheap, and it just comes down to quality. I mean, it's like they know what the secret sauce is to make something that's not going to break and with extreme precision. And that just comes with this fanatical obsession with precision. The same in Switzerland, and also the engineering skills they have are just top notch. And it's a field that a lot of Germans like going into, to become a mechanical engineer. And it's by the time well, they changed it a little bit now because they went to the US program with also having like, the bachelor's and the master's. But it used to be when you went to a German university, by the time you graduated, you had what I felt was the equivalent of a master's degree in the US. But the US only recognized it as like a bachelor's degree. And I'm like, these guys were in school for 7 years. They weren't there for 4 years. And they were required to do projects and internships at companies and stuff like that. That was like all part of that thing. So by the time they get out, especially the German school system, the gymnasium goes to 19, not to 18. You used to, not anymore. Used to have a year of obligatory service in the military. So that was like, so I mean, you couldn't start your university until you're like 20, and then it would be like a 7-year program by the time you get out. So you're like 27 when you're graduating. And I guess at that term, it's like, well, wait a minute. It's like, you don't become a productive member of society until age 27. We're going to do something about that. And so then they looked at the American program and said, oh, they can start graduating at 12, their 12th year. You don't need to have a 13th year. Yeah, you don't have to go, no more have the obligatory service. And so they're kind of cranking them out a little bit faster. But still, I think there's a lot to be said about the quality. Yeah, yeah. The other thing that Germany has that is they have a very, very good internship program. There's actually two schools that people go to, and there's the university, which would be equivalent to going to a university school, and then there's what they call the Real Technique, which in the U.S. it'd say, oh, that's like going to a community or tech school or something like that. For Germany, it's actually looking at it with a source of pride that it's like. And, unfortunately, they kind of screen the kids almost too early in age. It's like, oh, this kid will never make it to university, and it goes more in the university track. And the other's like, oh, this guy's is just going to be a technician. But the Real School, it's not community college. I mean, you come out of there really knowing how to work with stuff and how to build stuff. And so you get that combination of some really good, solid engineers, and then people that know how to actually, use a hammer and a screwdriver and a bunch of other equipment. Yeah, you get stuff that's quality built and reliable, and that's something that's been lacking in the U.S. And I know they've been trying to do a similar kind of apprenticeship program in the U.S., but it doesn't exist. So it's definitely a much better program that way. When you think about the quality of technicians you got to produce.
Well, I can't wait to have them in the podcast. I think hopefully we can manage to get them in the
Oh yeah,
podcast very
absolutely,
soon.
absolutely.
How about
I
them?
hope so as well. Yep.
Well, I think it was really fantastic episode as always. I think yeah, as I say, students just appreciating this series, the effort and the time to put to make this analysis detail. I'm blown away. I'm just myself. I'm learning first time also stuff. So I
Yeah.
deeply, deeply
Again, and it was
appreciate
like
it.
this morning. I just
Thank
saw
you.
the Neura. Uh, there was like a post that went out there, and I decided to go down. I was like in this rabbit hole. Oh, look at this, look at this. I was just grabbing screenshots and saying there's a lot to do here. So that's more or less like my hot take. And what I need to do is do like something a bit more in depth.
You should call this episode by the way because you came up with all the title, all in a head. It's all in a head.
Well,
Waste
this
not
one was like walk
want
this
not to serve.
way. So the first part is walk this way. But the second part, I have to come up with something for it.
Yeah, maybe something. You have a
Mhm.
great title, so I think
Mhm.
you need a great title. You didn't make a boss yet, so you still have to make a boss, or you did.
Yeah, I guess maybe the thing is like I've
Okay,
become a neurotic.
okay, great. I'll end it here,
Yeah,
and thank you
and I'll
so
see
much.
you later today.